Hello and welcome back to another festive coding session with Mr. Jacob. Today, in our Advent of Languages, where we strive to implement the same thing every day in the 24 first days of December in another language, we will implement this little program here, which should in the end display something like this or something that looks kind of like this little Christmas tree in ASCII format on the command line. And today's language will be ARM64 assembler. So I decided to actually go ahead and implement this thing in ARM64 assembler on my Apple Silicon Mac, which is actually an M1 Mac. But with a little bit of changing, this should run on any other ARM Linux-based device, for example, as well. However, the syscall conventions that we are using here are macOS specific, so it will not directly compile and work on a Linux, for example. However, of course, pull requests are welcome to the repository, which is linked below, down below in the description, as well as all the other videos, or the playlist, better said, with all the other languages that we already did until now. I have a little bit of preparation done. I have created a simple make file for us so that we can actually compile a file called helloxmas.s, which is the usual extension for assembler files. And we are simply putting everything here through the AS. So on macOS, this would be the Clang compiler assembler here, which simply reads our assembly file and outputs a Hello Xmas version of it by then actually putting it through our linker. So what we are doing is we are compiling this thing using the assembler, getting an object file, and then using the usual linker LD, which then creates us an executable. But that's everything that I've done. I have essentially set up our build environment so that we can get right into it. So let's get right into it. So let's create a helloxmas.s. And I have actually opened up two references that we might need during or while we are doing that, actually. So let me quickly show you. So what we have here is on the left side, actually, from the Apple's from Apple's repository, from their kernel source code, more or less, the file which contains all of the different syscalls that could be made. So essentially everything that could be directed back to the kernel to do some work that a user space program usually can't. So if you, for example, in a C program do something like printf, it will essentially in the end use some sort of syscall, usually write, after doing some more processing, which then writes this output to a file descriptor, for example, stdout and stuff like that. And in assembler, we have to do this manually because there is no system library that we could use to call all that. We could essentially link against some sort of standard library there and use that, but that would be besides the point. We want to do it ourselves here in this example. So what we will most likely need there is, for example, this write syscall. And we can see here in this table, for example, that the write syscall is the number 4. And what parameters it takes. Essentially, it takes the file descriptor as an int. It then takes a pointer to the buffer that it should print out and the size of the buffer in bytes that it should actually write to this file descriptor. And we have default file descriptors like 1, 2, and 3, for example, which are the stdout, stdr, and stdin. While I'm not sure, I guess stdin would be file descriptor 0. I'm not 100% sure there, but we won't need stdin actually. So we could look that up as well. So we have a list of all of our different syscalls, as you can see here, things that we can actually instruct the kernel to do. And we will see in a second how we are doing that. On the other side, we have the ARM A64 instruction set. So essentially what this is it's a list of all the different machine code commands that an ARM64 CPU actually understands. And it can be given to do whatever we want it to do. So those are all the different mnemonics. For example, we could search for something like add, which we most likely will need. So let's check here. What is that? ADC, add with carry. No, we simply want the simple add version here. So as we can see here now, there are different versions of this. There is add immediate, which takes an immediate value, which you can add to something which can be 12-bit long. And essentially this here, this is the description of what the bytecode looks that is in the end the assembler needs to generate for us and put it into the CPU to actually execute the command. However, what we can see here is what this command does and what parameters it essentially expects. Can I make this a little bit bigger? Yes, I can. So this is actually maybe a good way to look at something if we should not be sure how a certain command works or how we need to work with it. So we have those two references open, so let's get into our file here. And we need to start first by telling the assembler a little bit about our program. So we need to tell it that we want some sort of entry point, like for example _main, which is the default entry point of the Clang assembler, if I'm not mistaken. We need a certain alignment. We need to align our memory by, or our program by 4 bytes, and 2 essentially this is an exponent, so it's always 2 to the power of what we write here. So we want to align our program to 4 bytes, so 2 to the power of 2, which is 4, because ARM64 commands are always 2 bytes, so 32 bits long. Every ARM64 command is a 32-bit command, and we need to align our program so that this can actually be read properly, so that it can be read as a command after command after command, so to speak. Then we are simply telling this thing that we want a label, and those labels can be named essentially anything, and they are simple markers for the assembler which we can address later on to, for example, jump back there. Essentially what the assembler during assembly will do, it will mark the labels and store the memory locations of those labels and jump back and forth in the code for that matter. So what we need to do here is now something like, the minimal program we could do is, for example, we could somehow tell the system that we want to exit. And this is actually done via an exit sys call. So let's first of all do that to get going there and see how we can actually tell our kernel to do something. So in order to exit a program, we need an exit sys call. And so we check our list and we see here is an exit sys call that actually takes the return value as an integer. And as we can see here, it's code number 1. So let's quickly do something in our compiler here, which in our assembler, which is not essentially necessary, but it makes things a little bit more readable because we can define our own constants, so to speak, which are then kind of replaced during assembly with a value, for example. So what I can tell it here is that I want the name sysexit to mean actually the value 1. So the moment this is actually defining an immediate value. So I'm saying that I want this exit to be actually the value 1. Yeah. So in this exit now is the value 1. And I can actually now use this. So how do we call something into the kernel? There are processor registers. So our ARM64 CPU has registers and it can access memory. And it has essentially 64-bit registers, which can more or less be used freely. There are certain specific registers and specific registers which are reserved for some things and where some things are put in. It has a kind of aliases to these registers, which are a little bit special, like, for example, the stack pointer and stuff like that, or the return address once we jump into a certain function or something like that. But there is something that's called actually C calling convention or calling conventions for our system. And in macOS, the calling convention is actually that when we are transferring basic data, we are using the registers starting from X0 to X5 or X6. I think X6 is the one. So the registers are called X0 to X30 actually. And those are the 64-bit registers. We could actually access them in a 32-bit mode, but we will see if we really need that. So what I can do now is, by using this calling convention, as we have seen, we need to put into our exit call one argument. So one argument will be transported via X0 register. So before calling this function, we actually put the corresponding value into the X0 argument, X0 register for this function to process. So what we simply do is we use the MOV instruction, so to move a value into the X0 register, and we can here now put the value 0 because we want a 0 exit code, which is a successful exit code. Then we need to somewhere put the syscall that we actually want to call so that the system knows what to call. And in our specific case here, the convention says that this is expected in the X16 register. This, for example, is something specific to the macOS kernel. And therefore, we put in there our sys exit code. So essentially the reference ID where the kernel then knows, okay, if this is there in this register, then I should do this exit syscall operation. And now we need to kind of trigger something within the kernel from our user space. So we need some way to interrupt our usual processing and jump back into our system kernel, which then can do some work. And this is essentially done by triggering an interrupt, or in the ARM64, it is called supervisor mode or command. So that's SVC actually. And by definition, we are actually calling the interrupt here with 80. So that this initiates kind of our syscall. So if we now actually exit this one here and we store it and we do a make and hello Xmas, I hope this might work, and it of course does not, because unknown token in expression. I see. So I guess what I need to do here is I need to do it like that, most likely. Let's see. Okay, now this compiled, and as you can see, it executed and exited. And if I check the exit code, it is actually 0. Let's see if this really worked by simply exiting with, for example, an exit code of 1. So let's make this again. Let's see the exit code. And as you can see now, the exit code is 1. So our code actually works. So what we have done is we have actually done a syscall into our kernel to exit our program. Okay, I see. That's not very much. So we need to do some output there, but we have done kind of, quite something neat there. I'm just adding a comment there, which is done by using the semicolon here. Just to make sure that I, in the end, know what we are doing there. So now let's see. What we are usually doing is we are, or in our all of our examples before, we created some sort of a make tree or print tree or something function. And we can essentially do that here as well. Even though there are no real functions, there are only memory addresses that we can jump to. However, there is a certain convention on how to work with those addresses. And if we take, for example, the same convention by using the processor registers X0 to X6 or something like that for our parameters, for example, we can essentially define our own functions. So let's maybe do that by simply creating a specific mark here, a specific label, which we could call tree, for example, and this could be our tree function. And we can then jump into this function using the branch and link command of the CPU. And we then just tell the system that we want to branch and link to the tree label here. So that is essentially replaced by the assembler with a memory address when it is done, when it is assembled. So what does this tree now need? It must do a return command at the end, because what return in the end does is it jumps back to the memory address, which is stored in register X30. So essentially what we have here is, once we call this, it will branch into the tree or it will branch to the tree, so jump to the address of tree, but the link tells it, before you do that, please put the return address, so to speak, the address to jump back to, so essentially where this is here, into the X30 register, so that when the red command is called, then essentially this will take the X30 contents of the register X30, which is kind of a special register, so to speak, and jump back to this location and further execute code. So that is what's happening there. To ensure that we can do some sort of recursion in our method calls so that we can return actually this chain, we have to kind of make sure that we leave that intact. And therefore, it is a convention usually that you have a certain frame, you have a function frame, so to speak. So you need to set up the scope of the function by storing multiple things. First of all, you need to ensure that the stack pointer at the end of the function is the same as it was at the beginning. You need to make sure that except when you are using the stack to transfer data into functions, which can be used as well. However, the usual thing is if you do something to the stack to have, for example, intermediary memory somewhere to store something, then please restore it back to its original once you are done. You have to store the X30 register so that it is actually the same at the beginning of this memory of this code sequence here than it is at the end of the code sequence. And you should actually make your frame pointer, that's actually kind of the stack pointer after you have saved this frame there to X29, because the system expects X29, which is a special register as well, to be a correct stack frame. So those things are called stack frame, and you have to ensure that. And we can actually do that by simply using there is a neat command there, which is understood by the CPU, which is called store pair. And we can therefore store the pair of X29 and X30. Well, let's make this like X29 and X30. And we store that to the special position of the stack pointer, actually, minus 16, because the stack pointer actually needs to be aligned by 16 bytes. The stack pointer is always supposed to be aligned by 16 bytes on ARM64 systems. And as we need the memory anyways to store the 264-bit pointers here, this is actually good for us. So we take those 16 bytes off the stack pointer, and we are so making the stack bigger, kind of, there. And what we do then is we tell the system with an exclamation mark here in the end, and I hope that this is actually the correct syntax. I'm not 100% sure. We will see. That it should first store the data at the first decrement the stack pointer by 16, then store the data into this new pointer position, so that we actually have enough space there to store the data there. And after we have done that, we are moving into the X29 register, our current stack pointer, so that we always have a proper stack pointer reference. We might do something with the stack as well. And then we will simply move back in the end, when we are near the end of the function, we will move back into our stack pointer, the contents of X29, because we stored our stack pointer initially there. And then we use load pair to essentially load the X29 and X30 registers again from our stack now, by telling the system that we want to use the stack pointer now as it is, because we are at the beginning of this data, and then afterwards we want to increment it again by 16, so to make sure it is exactly at the same position that it was before. And this is simply the syntax of doing that. And if I've done nothing wrong here, we should now be able to call this without causing anything, actually. So let's see. Okay, this is not compiling because, as I've said, I might have done something wrong there. Okay, I see. If the syntax wasn't that, it was something like that. So it was something like that, because usually those brackets here indicate that we want to do something offset by something. So what I have said now is use the stack pointer address and offset it by -16. So let's try this again, and this works, and it still executes. So now it's time to do something with this. Essentially, what we can do is we can kind of save that somewhere up here for us, because I guess we will need that. We will need that. Come on, we will need that maybe some more times to do stuff. So we have something here to set up, come on, our stack frame properly. So every time we want to kind of define our function, which is not really a function, but if we want to define something like that, we need this code around it. So our tree, what could it do? Our tree should be, let's quickly maybe get get the base tree here so that we have something to talk about. And copy that in here. Something maybe like let me put that there. Let me remove the spaces here, and let me quickly add a comment there. And now we have kind of a reference there, what we are talking about, what we want to print. I guess those can go, because we don't want the ornaments here. It's complicated enough already, and the video will be a little bit longer because assembly is actually a little bit complicated, and I want to explain to you what I'm doing. So what we are actually now doing here is we need to first print those spaces, I guess. So we need a way of printing something to the screen. So let's maybe create, first of all, a new function there. So a label there, we could call that print, for example. And this print thingy here will print one character to the screen. And we expect this character to be in X0, I guess. So we would do something like print char C. This would kind of be the index here, which we would expect in a C program. So I guess this would be print X0 as character, or print character in X0 to std out. That's what our print thingy here is going to do. So let's see how we can do that. First of all, as I've said, we need to fix up our stack frame. So let's copy that in. So we have that now here and can actually create our function here like we wanted to. And I guess we need to do another this call there. So we need to write this call. So let's quickly go back to our write here, which is this one. It's write. There you can see it. And it takes, as I've said, the file descriptor, the address of the buffer, and the size of the buffer. So that's actually kind of neat. So we need some sort of buffer there. So we need a memory address and not a register. We can't actually use a register as a memory address. The things doesn't work like that. So we first of all need to make some space in our stack to store something in memory. So we are simply going ahead, and as I've said, it's always 16 byte aligned, 16 bytes aligned. We will simply subtract 16 further from our stack, so making 16 bytes space. We essentially only need one, but we don't care. Let's quickly make the let's then think on how we can actually load that. But before, let me tell you that this is exactly why we are doing this storing of the stack frame within X29, so that we can then restore that on the end of the function without thinking about how many space we might have kind of used or allocated in here. So just jumping back again and essentially giving this space back to our program. Okay, so we can actually set somehow 1 byte, but I'm not 100% sure how we can actually do that. We want, it is something like load. Where is my load? How was it called? How was it? store something like we could store something. Let's see. Yeah, that's not the best way of doing that. I think maybe we can just go. This is actually alphabetically sorted. Let's go to. There is something like store register immediate. That's something that where we can use something to store register byte immediate store. Is it actually that? Because what we want to do is store register byte. Stores the least significant byte of a 32-bit register to memory. Yeah, that's exactly what we want. So all of the things that store something in memory are usually starting with store. And we want strb. And strb actually takes a 32-bit register. So there we are. And then it takes the address where to actually store that. Okay, so then let's do that. I guess. So it was store byte, and it takes a 32-bit register, and we can actually access every of our 64-bit registers in 32-bit mode by simply using W instead of X as a naming scheme there. So we want to put that into into X0, because our calling convention for our syscall says first. No, that's not right. We want, let's see, this right. Where's right? It must be here somewhere. I'm not seeing it there. So first the file descriptor. So this will be actually X0. So this would be the memory address. That would actually be X1. So we want to write it to W1, which is the 32-bit variant of the X1 register. And we want to put the contents. No, wait. No, I need to think. That's not true. We currently have in X. So this is what we have. We have an X0, the character stored, which we should print out. So we need to first put this to the stack. Yeah. I confused myself. So we need to store the 32-bit character, which is completely fine because it is only a byte in the end. So we are reading this in 32-bit mode, and we want to actually place that at the current position of the stack. We allocated some space on the stack, and we are simply putting that there. So now we can prepare everything for our syscall, because now we are doing we are moving into X0 the std out file descriptor, which is actually 1. So we could actually maybe do an ASCII here for that as well. So let's define that as std out, just for to be able to better read that. So we can do here std out. And now we need to move into X1, the address of the memory position to actually give to the write call. So this would actually be the current stack pointer. This would be the memory position that we want to print out. We have put the character in there before. And now we need in X2 wasn't it length? It was the length, wasn't it? Yeah, it's the size. So in the size in bytes, which in our case always is 1 because we are only printing 1 character. And now we need to do the syscall here and tell the system that we actually wanted to do that. And now this should actually print something to the screen. So let's, in our tree function here, test if this is true. Let's move something into X0, a character, for example, an X. And now we might want to do a branch link to print. And we might want to do the same thing, which hopefully works now, with a \n as well, so that we can actually go to the new line just to make it a little bit more readable on the command line. And let's execute this within a VI here, so that we can actually do something like, hopefully, no, I did that wrong. Let's do it like that, hello Xmas. And nothing to be done for all. Okay, that's interesting. Why didn't this work now? Nothing to be done for all. Make clean. Make. And we want kind of do this. It didn't print anything, did it? So why doesn't it? Let's see. We should actually have, because we never we never specified what it should do. So we of course need to fill X16 register with the syscall for write, and we already figured out this would be 4. So let's put that there, and let's do this right here. And now it should actually, yeah, now it prints out this X with a new line. So we have already a working print function. What we need next is something that can actually print spaces for us, because we will need to repeat spaces a lot here. We will need to repeat spaces here and in between there. So let's quickly write that function for us as well. So let's call that space. And let's take our stack frame setup here as well. Let's copy that in. Let's remove the comments there. And now let's see how we can do that. First of all, we need some sort of loop there. So we take again as print spaces, print n spaces, which we take via X0 to std out. So what we want to do now is we have our space number in std 0, so we need some sort of temporary register that we can actually use, and we will use X9 for that actually, because X9 to X15 are kind of temporary registers which are allowed to be manipulated within function calls. So every caller must ensure that it does not depend on those without saving them before calling a function. So we can actually use this convention here. Essentially, all of those are only conventions. You could do it a lot different there, and if your program adheres to that, it would be fine. However, it might not be you might not be able to then reuse this part of the code in something else, for example. Okay, so what we can do now is we can move the contents, or let's maybe just for readability start at X10. We are simply moving what we got as an argument in X0 to X10. So this would be X10 equals n now, the number of spaces. So what we can do now is we simply do something like we do a loop. So we are essentially, we need a label here then, call that space loop, for example. And what we want to do is we want to essentially print a space. So we are moving in X0, we are moving something like the character, space. But for now, let's simply do an X, so to better see that we are doing the right number of spaces. And we can do it to do, come on, no, this is not, to do replace with space. Okay, so now we have done this, and now we need to branch and link to print, because we want to print this character. So we are essentially jumping into our print function there. And now we need to somehow decrement the number of spaces that we have been given. And if they are not 0, we should essentially do the same thing again. However, we might want to check this beforehand, because we might have given the number 0. That would make things actually a little bit easier for us. So I guess first of all, we should do a comparison here between between our X10 register and the number 0. And if it actually is 0, 0, so branch if equal, so if it is 0, then we want to jump to something like maybe space loop end. And we define simply a label here called space loop end. Yeah, that would do. And otherwise, it will simply go on and call this print function here. And then in the end, we are simply doing something like subtract from X10 and store it in X10 the number 1. So we are just going there, and then we are branching to space loop again. So back to up here. So essentially, this should now be a loop to print spaces. So let's start our tree by checking out if this actually works. We need to print first the number of groups minus the number of iterations in spaces here. So yeah, let's calculate that, I guess. So let's go ahead and do some sort of calculation here. And we might need to take into account that we are now in our spaces function using this x10. And as I don't intend to copy this over all of the time, it is a little bit easier to just know that this is actually destroyed here. So let's maybe put a comment over here saying destroys x10 so that we know we can't use it outside of it. So that is what I meant with, if we know what we are doing there, we can actually do things that are maybe not adhering to the convention. So I guess what we need to do now is we need to print those spaces out, but first we need to calculate them. We have given our tree function nothing so far, so we need to give it the number of those groups that we have here. So these two lines would be one group, this is one group, this is one group. So our example actually has 3 groups. So let's do something like move into X0 the number 3. So our register 3 is now register 0 is now 3. And let's then take this here and maybe store it in X11, for example. We know that we are not overriding that in our spaces function, so we could actually easily use that. So let's do an X11, X0 here. And let's mark that as X11 is now the number of groups. And what we now need is, as I've said, we need the number of groups minus the number of the current iterations. So we want to now kind of iterate from 0 to the number of groups, and we will do that in a second. However, we need to prepare something for that, kind of an I variable, so to speak. And we simply kind of start that here by using the same value as the 0 value, because we want to start at 0 there. So let me quickly mark that as well. X12 is the I value there for us. Now we need some sort of label. So let's call that group loop, because we want to jump back here again. And what we essentially are doing here is now we will work with our group loop, and let's do something like group loop, or let's give it a group loop end label, even though group loop end, even though we might not even use it, just to to see where this ends. Okay, so our group loop now needs to do what? It needs to print, as I've said, the number of groups minus the current I spaces there. So yeah, we can use another variable to another register here to calculate that. So as we need to call spaces in the end, we can actually use X0 now and store this directly there. So in X0, we are now storing first of all our groups data, which is in X11. Then we are subtracting from the thing here the X12 data, our I. So we have now in here, we have X0 is groups minus I. So after we have done that there, we can actually branch and link. So we can branch and go back again to call our space. We call it spaces or space? We call it space. Maybe we should have called it spaces. I don't care really. So now we actually have printed out the spaces. Now what we need to do is we need to put in our X0 our / character. Then we need to print that character. Now we need the spaces between the /forward and the /backward to build this tree shape. So essentially what we need now is in X0 again is this number which is between the spaces. And in this case, it's actually I times 2. We always need the group number we are currently in times 2. We now have a little bit of a problem there because we can't multiply with an immediate value in ARM64 assembly. So what we need to do is we first of all move our initial value, our I, into X0 again, so to use it. So we can use our X12 value, which is the current I, into our X0, which we want to pass to the space function there. And then we need to maybe put that into x1 because we are not using x1 and it's not a problem there. We can use that. So we put into x1 the immediate value 2 because we want to multiply the x0 there. And then we can do multiply x0 with, or we could essentially maybe do this here in one call. So we are putting into x1 the 2, and then we are storing the multiplication result from x12 and x1 into x0. That's actually possible. So we can actually there, make one instruction less. We don't really call this isn't the most efficient way to do this anyway. Okay, so now we actually have this I times 2 thing there in x0, which is perfect because now we can again call the space function, and now we have the spaces in between. Now we need to move into x0 the character, which is a backslash, which of course we need to escape here because it could be an escape sequence, and then we need to link up to branch and link to print again. After that, we need to quickly copy that because now we need to print a new line again, and now we have our first line. So let's kind of quickly see if this works. Let's remove this test code that we had before, and let's see if this actually now prints some sort of tree. It does not. So unexpected. I essentially missed a comma there, I think. Yes. Okay, let's see. So as you can see, we have our first line, but then we have something like a bus error, which is a little bit strange. That usually happens when we do something bad with our stack frames. So let's see if we somehow made something go kaput with our stack frames there. Let's see. Okay, this seems reasonable. Where do we manipulate our stack frame? Again, we do that here. However, this looks reasonable and we copied that over everywhere. So the only other position where we are really manipulating our stack is when we are allocating something on it to print something. So it's maybe up here. So I subtracted a negative value. This of course can't work here because we need to subtract from the stack value and not go into. Essentially what we did here is, even though I'm not even sure if this works from an instruction standpoint, this essentially moves up the stack frame into an area where we should not have been. So let's check. Okay, now this actually prints it out. However, it still does not loop because we have not implemented looping there. Okay, nice. Now we should actually doing our group loop. Wait, we should be doing our group loop, but we aren't, are we? Yeah, because we never implemented the group loop thingy here. So at the end of our group loop, we should actually compare our what is it, x12? Yeah, x12 is our I. So we should compare our x12 to the number of groups. So x11, we stored that in x11. And if x12 is still less than the number of, so if this comparison is a less than comparison, then we want to branch back to group loop, and otherwise it will simply continue. So if I have done that right, let's see, it should now never continue. Yeah, it does, because, come on, because we forgot to actually take x12 and subtract 1 from it. We forgot to extract 1 from it. Okay, still not working. What did we do wrong there now? No, we should not subtract, we should add. My God, assembly is always making me kind of a little bit crazy. Okay, so now we have the first line of our group there. So essentially what we need to do now is we copy this whole code here, which prints this line, and let's do something like second line here. So this will be first line. And there we now have a little bit of a different parameter. So what we want now is we want spacing, which is essentially the whole thing -1. So what we had before, that actually is okay. And then we are subtracting 1 from it as well. So now we have 1 less space. And this needs actually to be I plus 1 times 2 to be the correct spacing. So let's see how we can actually do that. Now, I guess we can't do it in this one instruction here, even though there is something like multiply add. There is a combined instruction for that, but let's not think about that now. Let's simply start by copying x12 into x0, then we can actually add 1 to x0 here, and then we can use x0 as a base here to multiply. So now this should be correct, and now let's see if we've done that. We should get our Christmas tree, and I guess we can now in our space thingy here replace our axis with real spaces to make it look a little nicer. As you can see, there it is, nice. And now, after we have our group here ended, we now need to print this line there, which we need in kind of the same way as we are printing spaces. So maybe we should do something like providing the space thingy here with a way to define what it should actually print here. Never mind. We can simply kind of steal that code, I guess, and maybe just use it directly. So let's copy that, and I guess we can still use the x10. Why not? And we simply put in there, what would that actually be? It was something like the number of groups times 2 plus 2, wasn't it? So, and this can definitely be done in one instruction. However, let's just do it like that. We had the groups in X11, if I'm correct. We had the groups in X11 here. So this is our register. So let's initialize it with that. Then let's do a multiplication. We need first to prepare our. We could do it. Yeah, I don't know, maybe with mm, hmm, where would we actually prepare that? Mm, maybe X13, or maybe we simply can use X0. We will override it in a second anyway, I guess. Yeah. Okay, that's fine. So let's use this as an intermediary register with the value 2 here. And now we do a multiplication of X10 to X10 using the x0 as a multiplicator there, and then we add to x10 and store that in x10 the value 2. So now we should actually have this there. So then we are actually iterating that one, and we want to print then and call that kind of, I don't know, maybe divider loop here, divider loop end, and we will branch to divider loop in this case, or to divider loop end in this case. And yeah, we are doing that, and now this might work. We will see. No, this was the wrong command. Yeah, and there we are. We have that one, and now so we only need our trunk there, and our trunk again needs some spaces. So we can do something like x0 equals the number of groups is actually the number of spaces that we need there, if I remember correctly. So what we now want is we want to simply go ahead and put that into x0, which would be the value of x11, x10, x11. I think we stored it in x11. Yeah. So we take x11 there. Where are we? and put that into X0. Then we do a branch link to space. Then we put into our X0, we put this character here, and we do a branch link to print, and then we do that again, and then we do that again with a backslash, which, by the way, we need after the divider loop as well, because what was that? Because we need a new line after this, and then now we just move that to the correct position and call that here something like trunk. And now maybe this prints our Christmas tree. And yeah, we need to do this trunk part twice, actually. I guess we will just copy that instead of creating another loop there. So we have our Christmas tree written in ARM64 assembler, and it was, yeah, as I've said, it was quite an ordeal, and it's not that nice to actually do that. However, now that we have defined it like that, we could easily go ahead and tell the system we want a bigger one, and it should still perfectly work and create us a Christmas tree. And I hope you learned something about ARM64 assembler. I learned something about it, and I refreshed my memory about ARM64 assembler a little bit here. And actually, I've never done a macOS syscall, so I actually researched before what the corresponding conventions were for doing a macOS syscall in ARM assembly. I've only done it on a Raspberry Pi before. So yeah, I hope you learned something. This is essentially how you program on the more or less lowest possible level of your architecture by really using the commands of your CPU. We are actually directly sending this to as a bytecode. We are generating a bytecode out of it for our CPU, for our ARM CPU to execute and to put something into its processor registers and to get something from memory and to write something into memory. And as you have seen, we have only used a very minimal subset of that. This document is actually 5,000 pages long. So the kind of starting point of ARM, which was to have a reduced instruction set, in that way, it's not that reduced anymore. It is still it's still the basic idea of it. Like, for example, all instructions have exactly the same length, like 32-bit and stuff like that, so it is easily parsable. It has a lot of features, like it can do a lot of branch detection, and it can do a lot of optimization and stuff like that. That's why ARM is so nice and energy efficient today. However, this is essentially ARM assembly, so that is, we wrote what the CPU is actually executing in the end, and it is creating a Christmas tree for us. So I hope you had fun, even though this was a longer session, and I hope you will join me tomorrow when it is the next step in the advent of languages, where we do all of this in another language again. So I hope to see you then. Bye!